Hello and good morning. My name is Gerald Friedland, and I teach at the EX department of UC Berkeley, Experimental Design of Machine Learning. And so I'm going to give you a short glimpse of it and what we can do with it. And I also have a startup called Brainome that uses these techniques. Yeah, that's me. So what I'm going to talk about is actually kind of interesting, very interesting for me, because I did a bunch of work in privacy before, and I actually didn't even think that these two topics would touch in this way. So one thing is, whenever you share data, you kind of need trust, right? It's just what it is. If you're a person and you just gave Facebook all your data, and then you just hope, they don't do really bad stuff with it, right? And then in the end, they do whatever. Trust was breached. If your business, we have mechanisms like NDAs and, all kinds of stuff, right? And the main essential reason for this is usually the typical thing that happens when you call a hotline. When you call a hotline, it's like, okay, we're gonna take this data for quality purposes. We're gonna record this. You realize that, yeah, that's the purpose they're giving you because it's the purpose that you'd like to hear. Reality is they can do with this data whatever they want, okay? So that's the point. And so that's the essential reason that when data is collected, we collect it for one purpose, and then we use it for anything else, right? Once it's out forever. The question is, could we change this, right? And of course, privacy has been worked on in many ways. And of course, cryptography is the first thing that comes to mind, but that of course requires trust as well, because now I have to exchange keys between two entities, and that doesn't obviously, that's the same high-level problem. Then we can anonymize. It's like, okay, cool, but we also know that has limits. Like, for example, when we cross-correlate, that was the whole thing with the Netflix challenge. Netflix released data, and they thought, okay, that's cool, because it's all anonymized. Turns out, just based on your videos, you can cross-correlate. And I have a publication out from a couple years ago where really, you don't need to look at people's tweets. Just what you need to look at is the timestamps, because you can correlate those timestamps and the locations with other social media, for example, that require ID like Yelp, and you immediately de-anonymize. There's a different publication. So anonymization is not enough, okay? And of course, a whole field was started after that happened. It was differential privacy, right? So let's go ahead and figure out how much noise we have to add such that sort of individuals cannot be picked out, right? But it does require the adding of noise and also substitutions. And while this is a nice mathematically rigorous way of doing it, there's not a lot of tools out there, and practically speaking, it's a hassle to still do that. And that will probably change in the next couple of years, hopefully. But what I'm showing you is slightly different. What I'm showing you today, and that's the overview, is basically how do we use machine learning in a way that we can enforce a purpose on the data. That means I can give you data that you can use all the machine learning you want on just for the purpose that we agreed on. You can only extract the information that I tell you you are okay to extract. You cannot extract any other information. Okay? And it's, again, we're going to go through this side by side, but the major idea is that I built a model of it, a memorizing model, and then I synthesize data that has the same characteristics, and then I use the model to label it. Now I have synthesized data that has never seen the original data, and the model labeled it. And now I can do whatever machine learning I want on that synthesized data, and I can show that the model you build on the synthesized data will actually perform equally or better on the original data. So basically, it's the same thing that you trained the model on the synthesized data as if you were training it on the original data. But, this is synthesized data. That means it never saw the original. And yeah, when we tried this with, pilot customers, they were like, but now we can't do any other correlation. And you're like, yeah, that was the idea, right? So So the advantage of this is, what I'm showing you is, again, data isn't actually shared. We don't share any data. Okay, you can keep all the data private that you want to keep private. We use synthesized data. And it's actually interesting because legally, that means actually the person who synthesizes the data owns it because they created it, right? So that's a real actual barrier, not just the technical one, it's also a legal one. And then, of course, because we labeled it and we built a model to label the synthesized data, we enforce the purpose. You cannot go and do anything else with it, but you only have that labeling. And then we need to talk about the properties of that model in a sec, right? And since the data is resynthesized, again, you may do other correlations, but you can never be sure they're right because, you know, it's synthesized data. And of course, we don't have any problem like we have in differential privacy, like what do we have to substitute or how much noise do we have to add. So I showed you something in quick. Let's actually take a step back. Why does this work? How does this work? And of course, I'm going to show you some results. And of course, there are limits to this approach, like to any other approach, right? And in order to give you why does this work, I need to take you back into a little, you know, basically into a 3-minute version of my one semester class. Let's think about things a little more general. So if I have a sequence like 2, 4, 6, 8, right? And the typical question is, what's the next number? Well, you're going to say 10. Why? Well, because in your brain, you created a rule, okay? And the rule is +2 or every even number. If I give you a sequence like 6, 5, 1, 3, it's a little harder. Why? Because it's the end of my phone number, and like any other phone number, unless you pay for it, it's a completely random number. That means you cannot infer a rule. That's the definition of randomness. Why is this interesting? Well, first of all, a rule helps us to generalize. That's ultimately what we need to do, right? So in order to say what's the next number of 100,000, well, it's 100,002 for the first one, but for the second one, we couldn't say, right? And so we'll have to understand what I'm going to explain, we have to always keep in mind what we do with machine learning is we extract a rule. And if it's a deep neural network, well, then it's a sum of a weighted sum of dot products that encodes the rule, okay? If you're using a decision tree, then it's the decision tree that encodes the rule, and so on and so forth. It's just a way of how to encode the rule. And we've done this a lot, right? So you can always create a rule. That's the other thing, okay? So can you always find a model? Absolutely. But it may be overfitting, and I'm going to show you how. So, but the most important thing is that's what we're doing machine learning, right? We're just replacing that brain that used to look at the data that was collected and came up with a smart formula with this, a finite state machine, right? That means we're now saying, well, let's not care about the person who did it, but let's care about the model. So now what gets famous is not Einstein anymore, but GPT-3, right? So that's what we're doing. We do machine learning. Let's think about this further. The interesting part here is I can understand machine learning a lot better because it's a finite state machine. Now we have an entire field working with finite state machines for years. And I'm giving them bachelor's and master's in computer science. So let's use computer science to understand how machine learning works. So what we have is on the left we have data, okay? There's always classification here, okay? For everything that I'm talking about today, it's classification. So on the left you have some data, and on the right you have some classification. And now you're building a model, a finite state machine. So the question is, how do we do that? How many state transitions do we need? Because a finite state machine, literally, it's just a set of arrows, right? And of course, the easiest finite state machine is I go and take this table on the left and say, well, if I have the input of row 1, then my output is the output of row 1. And if I input of row 2, then my output is the output of row 2. So if I take as many state transitions as I have rows on the table, I can guarantee a model. But what kind of model is that? That's overfitting. That's a dictionary or a lookup table. Whatever comes in that I've seen before, perfect. My dictionary has it, I give you an answer. But God forbid that, you know, a little change is there that I haven't seen before. So you have 0 generalization, right? It's 100% accuracy, 0 generalization. Or you go in and say we do the complete opposite. We create 1 state transition. That means everything, let's say, is the majority class. Everything is 1. Perfect. I can generalize to every input. It works every time. The problem, though, is everything is 1, right? That means my accuracy is kind of not very good. So what I have is maximum generalization, but only best guess accuracy. And now you can see where I want to be. Where I want to be is right in between there. There is a trade-off, you know, and in statistics it's called the bias variance trade-off. I would call it the memorization generalization trade-off. But basically is I don't want to memorize. I want fewer arrows than that. And also I don't want to overgeneralize. I definitely want more arrows to build data models that I have here implying. Nothing else but quantization. And of course, Tishby and others have already found out that you only have to do is connect to distortion theory. And then the curve would look like this for uniform random inputs. Of course, nothing is uniform random. And of course, that's also the pathological case. But I'm not going to go much deeper into here. But that's a little bit of the introduction that I wanted to show you, just so it's easier to understand what we're doing. Now, why do I need this? Well, because I need to define something that's generalization. Right now, the state of the art is that generalization is defined as, on a validation set, I get high accuracy. That's a good definition. The problem is, it's a post-hoc definition. I don't know what the accuracy may be before I actually measured it. If you want to know what the accuracy is before you measure it, you have to create a definition that is, you know, taking into account that compression, right? That you have a compression between the number of rows in your table and the finite state transitions in your finite state machine. And so basically, and again, there's more information, I can give you literature, that's the idea, right? You have the number of correctly classified instances, which actually is equivalent to the number of correctly classified bits if you have a balanced binary classifier. We're not going to go into more, just to understand that. Divided by how many state transitions would the state machine need to actually memorize it, right? And if you have as many state transitions as rows, again, you have 1 as generalization, which is not a generalization. But if you have a lot more rows than you had state transitions, then you have a good compression. Then it's like maybe 4 to 1 or 10 to 1, okay? And that's important. We need that sort of idea of machine learning as compression for the rest of the talk. That's why I do this little theory thing. So it's a little more complicated than that, because we can show, for example, that if you have large dimensionality, even the generalization of 2 to 1 can still overfit, but we're not going to go there. So let's just agree for now that if you have a lot of correctly classified instances for very few state transitions, you're generalizing well. And then obviously you're going to see that validation accuracy is high. So if you want more on this, by the way, not only do I have a tool that will measure all of this for you and create machine learning models based on this, but also there's a whole class that I'm teaching is experimental design for machine learning. And there's also a cool app you can use to try this all out. So now let's get back to our privacy enforcing a purpose on data. And I'm just going to explain it, but I'm going to use the concepts we just learned to make it more clear. The first thing we need to do is preprocessing, right? So you give me some data set like Titanic. It has strings in it. It has, you know, categories in it, Boolean floats. What I will do is I will say, I don't care about all this human stuff. I care about the information content in each column, and I want to keep that constant and not change it, because that's what's important. And so I substitute everything with numbers, keeping the information content, okay? And that's kind of cool, because now I'm dealing with numbers, and not only is it that, you know, scikit-learn and PyTorch and all the tools I can use only deal with numbers anyway, but also I have a minimum and maximum in each column, which I can save, okay? So I do that, and then I put those aside. And what I then do is I train a memorization model. And that's something we just have to swallow. We have to swallow. It's like, what does that mean? What does it mean is I test on the training data. I don't use a validation set, and I absolutely force it to 100%. But also, I don't over-parameterize. I try to find the smallest amount of parameters because I still want to tease out generalization. Okay? So I want a high generalization ratio, the highest I can get, while getting to 100% memorization of the training data. And of course, our training data is our input data that we're using, actually, that we want to basically privatize, right? What this gives me, obviously, is a machine learning model that, let's say, has a 5-to-1 or so compression ratio. Why is this important? Well, because that machine learning model represents the data, has all the information in it, just like a hash table, except I can't reverse it. Because if 5 rows of my data represent one state transition, I cannot go back. It's like 2, 4, 6, 8. And I give you the rule plus 2. It's a highly compressed rule. You cannot go back to 2, 4, 6, 8. You may have learned the rule plus 2 with 10, 12, 14, 16. You don't know. And that's the interesting part. We have a rule now that's much smaller than the original data. That means you cannot go back to the original data, right? So that's, first of all, a privacy guarantee. But then you could say, okay, but just share that model. And if actually, that's a totally fine approach, okay? But practically speaking, sharing the model is often difficult. Like, you know, it's like you have this PyTorch dump, and now what, right? So what we do is, instead of sharing the model, we actually create and synthesize data. What we do is we take the min and max of all the rows that are before, and all we do is we generate numbers between the min and max. However, we need to highly, highly oversample. Why? Well, if you think about that, you have a cat and the dog detector, and the cat and the dog seem to be private. Obviously, the min and the max of the pixels could be anything, right? I mean, it's going 0 to 255 each pixel, but so you need to oversample. Why? Because then later on, when you build a machine learner, you will learn other rules as well that don't fit, but that doesn't matter. So you want to make sure that the rule is represented in your data. So you massively oversample that data. And then once you have the data oversampled, you need to label it with your memorization model. That's all you have to do. And now you have a new data set. You have labeled data that looks exactly like the data you had originally, except it's not. It's completely synthesized. And I give that to whoever I want to analyze my data. And by the way, I can, and also later we can, check that that labeled synthesized data is actually of any value by training a machine learner on that labeled synthesized data, and then using the machine learner on a validation set that I derived from the original that I want to keep private, right? And of course, that is how I check that this approach is valid. And it turns out, yeah, these are just 3 examples. We tested a bunch. If you create a model, and sometimes actually even worse, if you create a model on the original, you see this is the second column, you get 72% accuracy, 95, 98%, just doing regular machine learning. And then, because it's over-synthesized, you sometimes even get slightly better results. And I can't actually yet explain why this is so nicely and works so well for the earthquake data set. But we've tried it a bunch of times, and it turns out, yes. If you create a model that has never seen the original data and train on the labeled synthesized data, and then use that model to classify on the original data, which again, you shouldn't be seeing, but just to test it, you get better accuracy as the original. Sometimes, right? And so that gives you a very valid approach. And the funniest thing is that data, there's nothing you can infer from it otherwise except doing exactly that model. So, wow, what's this? Well, let's talk about what's not working, okay? So it only works for classification, right? I just gave you a whole framework but it only works for classification. You actually have to label the data, right? So the idea is we are encrypting, we are encoding, highly compressed, the function that is implied by the data. That means the data needs to imply a function. That means it needs to be supervised and labeled. And right now, it only works for classification. Now, what I want to do also, sort of the next work in the scientific realm, is to actually show how that maps onto differential privacy, because it should. The generalization ratio itself is basically, if you convert that to decibel, you'll see that's basically the minimum of the maximum of the average maximum amount of noise you can add before decision changes. So that gives you exactly sort of a range, just like differential privacy has. And then I think one thing I want to do at some point is to not just trust the theory, but also ask some hackers to, can you break it, right? But I'm very confident in it right now, at least. So, other than that, yeah, I'm opening this for question. Thank you so much for listening.
Yes, so you spoke about privacy. So obviously you're trying to compress as much of the information from the data into your model, but I still don't understand really how you can guarantee, for example, let's say you're trying to train how people vote, and you're trying to have, let's say, zip codes in as one of your inputs. How do you guarantee that you don't have a situation where a single zip code leads to a single person, and then your model can then predict how that zip code would have voted, and that you don't find that generalization in your compressed model?
Well, you have to think about this. You will never find that there is a single zip code. The attacker would have to try that out would have to find that with guessing and checking, right? So if you had, let's assume you have a single person with a single zip code, right? So you cannot look at the model and see that. It's not there because it's highly compressed. First of all, you can guarantee by looking at it that you can't see it, right? That's the second one. But the other thing is, in order to find this, you would really have to guess and check and go through asking the model about that zip code.
No, but maybe in voter registration records, I know that there's only one person in this zip code. How do you guarantee that the model didn't pick up on that?
So the model will have, obviously, the answer encoded, right? So whatever your question was, that's the first thing. It's about the question that's answered, right? So you cannot correlate a single zip code back to any other question, right? It's a labeling, right? So you will find the answer for that single zip code, whatever the question was.
Yeah, and I already know that there's only one person in this zip code. I know that from voter registration data. Now your model obviously will tell me the right answer, right?
Yes, but the other thing to do is...
So where's the privacy?
Well, no. It gives you you are okaying that for this purpose, you can give the answer. Remember, you're encoding the function, not the data. So you cannot correlate your single person zip code with anything else. You can only correlate it with the answer. So you're okaying, the contract is, I'm okay with inferring the labeling. Right? I get that.
Actually, I think the point is if it's a one-to-one mapping with the correlation, then you have a problem, right?
Yeah. Okay. Yeah. So if you're saying you don't want, I think your case they're trying to make is if you don't want a single person to be correlated at all, but that will be basically your problem is then you shouldn't do that, right? I mean, it's basically. Yeah.
How do you guarantee what level of privacy you're achieving? Like if you say, I don't want to map one-to-one, how do you achieve that when you actually map exactly the data to your model?
Well, because you have a generalization. You're mapping lots of rows. I mean, all you see is some compression that you can't undo. It's a one-way compression.
It seems like in your data preparation, you maybe have to say, how many people do I have in a certain zip code and remove if I have less than that many?
Think about this as a hash table, right? So you can ask a hash table, is this correct or not, right? By calculating the hash function. But I'm giving you the hash. I'm giving you a list of hash codes. You can't go back to the passwords, or you can't go back to the input.
I'm not saying you can go back. I'm
Yeah. Yeah, okay.
We can take it off.
Yeah, we should take it offline. Okay. Yeah. There was another question there?
Yeah, I think there's a question.
Hi, thanks for the presentation.
Yeah.
In your previous slide where you demonstrated the experimental results with a star accuracy of 99%, have you tried in more complex data set with more variables like iris? Iris, for example, is one with only 3 variables, and you kind of rely on exhaustive enumeration of training data based on min and max. So how would this scale with, I don't know, 1,000 input features on a problem that it's not really kind of solved?
It scales. I mean, so not sure why that is a problem.
Because essentially Iris has only 3 input variables.
Yeah, Iris is 3 and Bank is 4, but the earthquake is like 20,
so
25
if we go to
or
2,000, which is like...
Yeah, I mean, we go to 1,000, we go to 1,000. I mean, I've done it too. There was some genomics data. We had like 15,000.
And in the way that you sample data based on min and max, so you break perhaps some conditional dependence between input features, doesn't this...
Well, the conditional dependence of the input features is what the model has, right? So you get to the labels. But the conditional dependence, and that's the important, I think it's almost similar to the other question. The conditional dependence between the input feature with regards to your output function is what your model models. That's not something we model in this step, right?
Thanks.
Yeah.
Hi, thanks a lot for the talk. I have a couple of questions. So the first one is, could you maybe give some case examples, like what kind of business analysis could your approach be used for? So like you generate the synthetic data, you give them out for analysis. Which kind of analysis could that be?
So I think the most interesting use case practically is as weird as this sounds, government contracts, okay? So what happens in government contracts is you get the data for like the time the government gives you the contract. But if you're in a research institute, or then you often want to keep the data, right? Because it's like, okay, the contract is over, but I still want to keep the research going on. And what you do is, instead of keeping the government data, which obviously would be breaching some law, you say, okay, I don't keep the government data, I synthesize my own data in this way and keep the research going. Yeah.
So as far as I understand, you choose models capacity, so it somehow accounts for the kind of patterns that you want to be able to analyze. Is that correct? So, so the question is, if you decide on the compression level and on choosing the model's capacity, how can you guarantee that the model that you, like the synthesized data that you get, accounts for all the patterns that you want to be able to analyze?
So I cannot, this is, so, okay, so first of all, what we do is we get 100% accuracy on the memorization model with the smallest amount of capacity possible, right?
Okay, okay.
Right, so that's the trade-off. This way we get a generalization, so we can't have a one-to-one mapping.
So you continue training models and validating those until you get like almost 100%.
Not almost 100%. Actually,
Well, here it's almost, no?
Okay, so no. There's two kinds of model. One is the memorization model, where we reduce the capacity as much as we can,
I see.
but to get 100% accuracy.
The memorization one is the one where you validate on the training data.
Exactly. But we reduce capacity so that we get a generalization, so we can't have a one-to-one mapping back to the data.
Okay, seems fair.
Right, okay. And then whatever happens for the build prediction model, that of course is the research, right? We don't know. I mean, you can do whatever you want. But the problem is, again, you're doing that on synthesized data, so you can never be sure that whatever you infer from there is right, except for what we do with the exact function that we have memorized in the model. Yeah.
Well,
Yeah.
this is being recorded. Yeah.
Okay. Okay.
Thank you. Very interesting talk. Could you explain, you said you can't, so could you explain why the earthquake example get such a big improvement?
So I'm working on explaining that, to be frank. But I think what happens is the original earthquake data was 10,000 samples. And the synthetic version is 100,000 samples. So we usually oversample by quite a lot, factor 10 to 20, in fact. And what happens here is that I think, so here's what's interesting. So the memorization model, right, gives you obviously 100% correct answers for the exact input samples, plus minus generalization tolerance that we know we have maximized based on our approach. Now what happens is if you have 10 times more samples, then actually you have a lot more data that fits that bill, that it gets to the original rule, right? So we actually synthesize data. And so that's why the prediction model that we built based on that actually gets a better rule out because there's more data. We just increased n artificially, right? And what I think happens though is, of course, what we also see is that this prediction model, and I haven't said that yet, is actually needs a lot higher capacity than the memorization model. So what happens is you often have also a factor 10. The way we explain that is that because we have the synthesized data is not just representative of the original data, exactly that's the point, it contains a bunch of stuff that the original model has never seen, and since the memorization model, it doesn't generalize that well. What happens is that it learns a lot of rules that are irrelevant for the original data. It learns a lot of rules that are garbage. And so however, it also, because it's oversampled, learns the rule that's relevant, so we get a high validation accuracy on the original data back. That's as far as I am with that investigation.
Cool. So, I mean, this is absolutely fantastic stuff, you know, with most of us being data owners and kind of wanting that protection from the other side of it. But a barrier to implementation I can see would be that companies would be, or government institutions would be reluctant to do so because under this current model, I can't really see a way that there's no guarantee that the data owner hasn't manipulated, say, the memorizing model or done that process in bad faith to skew the ultimate prediction model in their favor. So maybe a bit premature, but have you guys perhaps looked at ways to ensure that the, you know, on the getting up to the synthetic data is done in good faith and done such that it won't skew the prediction model at the other end in someone's favor?
Yeah, so what you can do is the left entity on the left can obviously do the same experiment, right? So I put that on the right, to build a prediction model and then validate against the original data. But the way to do it is to also check that basically what you can do is you can keep the validation data or test data secret. And when you contract out to other people, what you judge them on is how well they do on the held out test data that you only know that has the original content in it, right?
But I think we've talked about this.
Yeah, we talked about this.
To some extent, the data owner has to be involved in this process. Yeah. In the sense that yes, they are accepting that they're running tests on their side. And
of course, there's always a little bit of a compromise, right? Because now it's super secret stuff. Like, yeah, it would be nice. It's not, I mean, we had data scientists telling us, yeah, and now I can't see anything. It's like the strings are all numbers and so on. Yeah, sorry. That's the point.